Problem 611 is very similar to 610. You have a vehicle that's traveling at a speed of 15 meters per second, and you're going to bring it to rest in a distance of 2 meters because there's an impact. The difference between this problem and the previous one is that they are looking at the forces on the person inside the vehicle. The person is traveling at the same speed as the vehicle, so you can make that assumption. And at the end of the collision, the person is brought to rest as well, along with the vehicle. So you're looking at the average force exerted by the seat belts on a 90-kilogram passenger in the car. So some zeros that you can write down for this in the conservation of energy equation. I'm not really sure if we should call it conservation of energy because we have work. Let's call this the work energy equation. So the initial potential energy plus initial kinetic plus work, final potential energy, final kinetic. This is 0 because it's on a level ground. The MGH term is 0 both before and after, both at the beginning and end of the problem. You bring the person to rest, so their final kinetic energy is 0. Not too surprising, it's very similar to the last one. If you look at their solution, it's the change in kinetic energy is equal to the work. You know, they kind of skip a bunch of steps to get to that. I always recommend starting off with the work energy equation so you don't leave anything out, like the potential energy term. There's the final kinetic energy, which was 0. The initial kinetic energy here, a minus sign. The work is force times distance times the cosine of the angle between them, the angle between the retarding force, and the displacement is 180 degrees, so the cosine is -1. Solving for F, you can find the force of the seatbelt on the person in kilonewtons.